In this video, we're going to see an application of double integrals, and that is the volume of a solid bounded by two surfaces. So we're going to look back to our Calculus 2 as inspiration for this. In Calculus 2, you were asked often to find the area, not the volume in this case, but the area of a region R that was bounded by two functions f of x and g of x typically. And what you went and did in Cal 2 is that you found their points of intersection, or the x-coordinates at least of those points of intersection, A and B. And the formula that you were probably given, maybe with absolute values, maybe not, is that the area of R is the integral from a to b of f of x minus g of x dx, where you're really sort of thinking of the top function minus the bottom function. But I want to go a little bit further with our interpretation of this, and you'll notice here it says shadow. So what is that talking about? You're integrating from a to b. Well, a to b, if you sort of imagine it here, that interval AB is the shadow of that region R down on the x-axis. And that is kind of the inspiration. I put this in thought bubbles here, right, as a sort of a not very formal kind of formula. But that formula, that idea of doing the top function minus the bottom function over some sort of shadow, that is going to be our inspiration going into R3 one dimension up. So now if we look at Cal 3, if we look in R3 and we want to find a volume, so one dimension up, instead of finding an area like in Cal 2, we're going to find a volume of a solid here that I've called S. S is bounded above by a function f of x and below by a function g of x. And the volume of that solid S is going to be the double integral over this region D, we'll talk about D in just a second, of f of x minus g of x dA. And that double integral can be calculated using any of our previous techniques. Right, so you can set up that region D as a type 1 region, as a type 2 region. You might do it using polar coordinates. It just becomes a double integral. So let's talk about this D. D is this region here, which corresponds to the shadow of the solid on the xy plane. And so the memory aid formula, the kind of informal way of remembering how to find the volume of this solid, is here. It's the double integral over this shadow region D of the top function, now a function of two variables, minus the bottom function dA. And so how do we find this region D, this shadow region? Well, up here what we did was we found the intersection points. And it's going to turn out to be exactly that same sort of thing that we need to do to find D. We're going to have to find intersections of these two solids. So let's go ahead and look at an example where we put this to work. So in this example, we're asked to find the volume of the solid that is bounded by the surfaces Z is equal to 2 minus x squared minus y squared, and z is equal to 1. So how are we going to do this? How are we going to start? Well, the first thing to probably do is to use this formula up here, this memory aid. We need to know what the top function is. We need to know what the bottom function is, and then we have to deal with this shadow region. So to do that, I suggest that you try and sketch the surfaces. Certainly to the best of your ability, but a lot of the ones that you're going to be given are going to be surfaces that we've seen before in this class. And then it'll be sort of easy, or easier anyway, to determine which is the top, which is the function, the bottom function, and to get a handle on what this shadow region of the solid is. So if we go and look to the first function, z is equal to 2 minus x squared minus y squared. That is a quadric surface. That is a quadric surface that we learned was a paraboloid. And that paraboloid is facing downwards because of the negatives in front of the x and the y squared. And its maximum value is here at 2. So its vertex is at 2, and that paraboloid is facing downward. The other surface that we wanted to graph, the other bound, is z equals 1. And z equals 1 is just a plane. It's a plane parallel to the xy plane. So if we look here, there's our plane graphed in blue. There's our paraboloid graphed in red. And the intersection that we're going to have, right, if we look at the intersection, it's there. So the bottom of the surface is going to be here, and the top of the surface is there. So if we look over and extract sort of just that region, there is our surface. There's the surface that we want to find the volume of. So now at least we have an idea that our top function is going to be the paraboloid. Z is 2 minus x squared minus y squared. Our bottom function is going to be the plane. So the bottom is going to be z is 1. And then what we have left to do is to figure out this region D before we can iterate. So to figure out D, we're going to proceed just like you would have in Calculus 2. We're going to use the comparison method, set the two functions equal, and see what comes out. So if we take the paraboloid, 2 minus x squared minus y squared, and we set it equal to the plane, z equals 1, bring everything, sort of the variables over on one side and the constants to the other, we're going to find this equation. X squared plus y squared is equal to 1. Well, that's our region D, or at least that's the outside boundary of our region D. So there we have our region D here graphed in R2. X squared plus y squared is equal to 1, and now we need to integrate. So we're going to do this formula. The volume is the double integral over our region D of the top minus the bottom dA. And we can proceed using any of our previous techniques, and so we notice that this is a circular region. A circular region which probably is going to lead us to use something that makes circular regions easy, polar coordinates. So we have the top function that we said here. We need to convert the top function into polar coordinates. So the top function 2 minus x squared minus y squared. So we're remembering that that is because r is x squared plus y squared. There was our formula from polar coordinates. So we're plugging that in here, and so we get 2 minus r squared. Our bottom function, z equals 1, well, there's nothing to change about that. So when we do the top minus the bottom, when we do top minus the bottom, we're going to have 2 minus r squared minus 1, or 1 minus r squared. We also then need to determine the inequalities which cover our region D in terms of polar coordinates. So if we go for theta, we want 1 full revolution of the circle. So theta is going to go from 0 to 2 pi. We want the radius, which goes out from 0, and fills out the entire region. So we want the radius that goes from 0 out to the boundary, and the boundary is the circle r is equal to 1. And so our inequalities for the radius r is 0 is less than or equal to r is less than or equal to 1. So we put that together all into this formula again. Volume is the double integral over d of the top minus the bottom dA. And we get the integral of our theta values here from 0 to pi over 2. The integral of our r values here from 0 to 1. The top minus the bottom here gave us 1 minus r squared. And then r dr d theta is the dA of the integral, right? That is dA sitting over here in polar coordinates. So we go ahead and integrate. This is a nice integral that does not mix the r and the theta, so we can pull out the theta in the first integral, 0 to 2 pi of d theta. We can multiply in the r and get an integral from 0 to 1 of r minus r cubed dr. Fundamental theorem on both of them. So the antiderivative of d theta is just theta. The antiderivative in terms of r, 1/2 r squared minus 1/4 r to the fourth, r to the fourth. And so plugging in here the top value minus the bottom value, and we're getting 2 pi minus 0 times 1/2 minus 1/4, which is 2 pi times 1/4, 2 pi over 4, or pi over 2 units cubed.